Okay, so thank you for the introduction. I am with the Information and Communication Theory Lab at TUE Eindhoven, and we're going to be presenting our work in collaboration with Marvell Technology. So first, the motivation on this problem is that we want to study IMDD systems, so we need to transmit a PAM constellation. In the example here, we're going to transmit a PAM6 constellation where we transmit it through an AWGN channel. The noise variance per symbol is going to have a distribution, it's going to be the same per symbol, so the channel is going to have a noise distribution that looks like this. However, if we now employ geometric shaping, we can play around with the locations of the points of the constellation. And if we optimize it for a given SNR, we obtain a constellation that it looks like this, where now the 4 inner points are more close towards the center, while the outermost points are further back. And by doing this, we can close the gap to the capacity of the channel, and we're able to save around 0.2 dB in terms of SNR. However, for the optical systems that we want to study, we have to deal with noise that is more complex. And in our scenario, now the variance per symbol is going to have a second component that is going to depend on the square of the amplitude of the symbol. And that's going to be given by the relative intensity noise. So instead of having a noise distribution that it looks like this, we're going to have a noise distribution that it looks like this, where the noise variance is going to increase alongside with the amplitude of the symbol. So the question for this work was, what are the gains that we can achieve with geometric shaping? And keep on going with the context. As I said, we want to study IMDD systems for intra-data center interconnects. So this application uses IMDD for the low complexity in transceivers and also the low power consumption compared to coherent transceivers. As of now, current commercial solutions have achieved up to 200 gigabits per second per lane with using PAM4 modulation. However, there's a need for achieve even higher data rates for this type of interconnections inside data centers, especially with the exploding domain of AI applications. So what are the main limitations for achieving a 400 gigabits per second per lane? For the principal one is to the electrical bandwidth of the components. Since if we want to double the capacity, we need to double the bandwidth, which is very challenging. So a solution for this is to increase the modulation format in order to increase the spectral efficiency. But modulation formats such as PAM6 or PAM8 have less noise tolerance due to the higher number of energy levels. In order to counter-effect the noise, however, we can increase the optical power, but in our scenario, we're going to be limited by relative intensity noise, which is going to be one of the main dominant factors for achieving 400 gigabits per second. So the contribution of this work is that we employ geometric shaping in an IMDD optical link subject to the presence of RIN. And we propose an optimal geometrically shaped PAM6 constellation that allows to relax the laser ring parameter design by up to 3 dB. So the IMDD system that we're going to study is shown here. We're started by the transmitter side. It consists of an externally modulated laser at a wavelength of 1310 nanometers, and it's going to have relative intensity noise, which is going to be the main source of signal-dependent noise. And then the X is going to be our PAM symbols, which are going to be the signal that drives the electrical to optical modulator, which in our case is a Mach-Zehnder modulator. And this modulator is also going to impose a peak power constraint into our system. For the transmission, we're going to use a fiber on short reach application, so there's going to be no optical amplification. And also, since we're operating at 1310 nanometers, the chromatic dispersion will be negligible. So we're only going to consider attenuation effects. At the receiver side, we're going to have a photodiode to convert the incident optical light, and then it's going to be converted to voltage and amplified by a transimpedance amplifier. And during this conversion process, electrical noise will be generated, which is modeled as AWGN, and this noise is going to be signal independent. And finally, the output of the TI is digitized, and we obtain our channel output Y. So the entire IMDD system from before can be modeled as a memoryless channel with additive noise given by equation 1, where X, as I mentioned, is going to be the PAM symbols taken from a set of M elements, and the noise is going to be modeled with a with Z, which is a zero mean and unit variance Gaussian random variable. So the variance of the noise in this channel is going to be given by the right-hand side of the equation 1. And then the noise variance is going to have two main components. The first one is going to be the contribution due to thermal noise, which is the same as the electrical noise. And it will depend on the parameters G and NEP, which are the gain and input referred noise of the TIA. And the second component is going to be the x squared times sigma ring, which is going to be, where sigma ring is going to be calculated directly by the ring parameter of the laser. And in both cases, the noise variance is scale up with the bandwidth of the system, which depends on the symbol rate. So for the channel model from before, we can obtain the average error probability, which is given by the equation 2, which comes from using optimal thresholds for a system with unequal noise variance, which can be seen in the denominator of the Q function, that we have the summation of two different noise standard deviations. And we're going to use this function as the cost function for optimization of geometric shaping. So we're going to minimize the symbol error rate for all the points on our constellation, subject to the following constraints, where the two first constraints correspond to the outer two most symbols, which are going to be limited in amplitude due to the peak power constraint of the system. And the third constraint defines the arrangement of the symbols within the constellation. So for these optimizations, we employ gradient descent methods, and the results are going to be shown next. So for the simulations to that, we use BAM6 at 400 gigabits per second as the baseline for simulations. We also consider an FEC overhead of around 12.9%. And we're going to measure the optical power with the OMA, which is going to be defined as the difference between the maximum and minimum optical power values. And something to highlight about this model is that the electrical noise variance depends inversely proportional to OMA, and this is due to the fact that the gain of the TIA is going to be changing depending on the OMA of the optical signal. And we're going to simulate for different ring values ranging from -150 to -141 dB over Hertz. And we also include a pure AWGN case, which is equivalent to the case where the ring parameter tends to -infinity. For the simulation parameters, we are given in the table here, which are a standard for the IMDD link shown here, and to achieve the 400 gigabits per second. So for the results, we have two main figures. On the left, we have the optimized prime constellation, denoted by X star, and at the right, we have the symbol error rate. At first, we show the results for where ring has a value of -infinity, which is exactly the same to the AWGN channel. And for the optimized constellation, we have that the solution is a equally spaced constellation, and the respective symbol error rate is shown on the right. Next, we simulate a finite ring value of -150 dB over Hertz, and we can see that for an equally spaced constellation, for the symbol error rate and represented in the dotted line, now the error probability starts to flare and it starts to deviate from the gray curve, which is the AWGN channel. When we apply the geometric shaping optimization, we obtain a constellation that looks like the one on the left. And we can see that the four inner symbols start to deviate towards lower amplitude values. And if we use this constellation, we obtain the symbol error rate on the right, which we can see that the symbol error rate improves and tends closer to the gray curve, which is the AWGN channel. Next, we also simulate the value of -147 dB over Hertz, and we can see in this case more the trend that the ring has on the channel is that it starts to converge to a certain value until it results in an error floor in the symbol error rate. Nonetheless, if we optimize for the geometric shaping, we obtain the constellation on the left, which follows the same trend as before. And now we can see that the symbol error rate improves. And we can even match the performance of the system with a lower ring parameter, in this case, -150, which is the orange curve, at around 3 dBm. Next, for -144 dB over Hertz, we're going to see that we obtain a higher error floor. And for the optimal geometrically shaped constellation, we see that once again, we're able to match the performance. I mean, we're able to lower the simple error rate and match the performance of the system with a lower ring parameter at around 3.5 dB here with the intersection here. And if we take a look at the constellations on the left, we see that they follow the same trend, but now as the ring parameter increases, the inner points start to deviate at lower OMA values, and this is due to the ring that it starts to become more dominant for lower optical values. And lastly, we have the results for minus 141 dB over Hertz, which follow the same trend as before, just now that the error floor is higher due to the higher ring parameter, and also the gains that you can achieve with geometric shaping are also lower. So from these results, the main conclusions that we can extract is that if we employ geometric shaping, we can achieve the performance of a system with a lower ring parameter, as we can see from the jump from the green curve to the orange one, and also from the red curve to the green one, which represents a 3 dB lower ring parameter, which is very important for this system, which one of the focus is also to employ low-cost components for the transceivers. So finally, take-home messages. We have an optimized geometrically shaped PAM6 constellation can improve the simple error rate of the system for this specific system that has signal-dependent noise. And this improvement allows for a laser design relaxation due to the higher ring parameter tolerance of up to 3 dB. And as for future work, we're going to extend this work to a PAM6 implementation via QAM32 in order to analyze the bit error rate probability. And also, we're going to extend the geometric shaping study to IMDD channels with memory and also subject to ring. And thank you for your attention.